Okay, guys. So I want to start this stuff about quadratic equations. Now, there's a lot of procedural stuff that you guys already know. You know how to factor a quadratic equation. Like x squared plus 5x plus 6 equals 0. You guys know that breaks down to x plus 2 times x plus 3 equals 0, and you get your solutions, right? My main goal today is to talk about like the general format of a quadratic, and also then talk about these procedures that you've been instructed on how to do, you've been shown how to do, and you've mimicked those processes for now over 2 years. Today, I'm going to show you why that stuff kind of works, okay? And my view is, if I can show you the why, show you the how, show you all the underlying procedures that govern a concept, then I should be able to throw any problem in front of you and you'll be able to solve it. Does that make sense? It's the idea, you know, give a person a fish, feed them for a day, teach them a fish, feed them for a lifetime, right? Okay? So I don't want to just show you the steps and you mimic them, because you're only then going to be able to solve problems like that one, okay? But if I show you or teach you all these underlying things and all this stuff, all the theorems and stuff like that that attach to it, then you should be able to come in contact with any quadratic equation and deal with it successfully. Does that make sense? Okay. So, do we know what the quadratic equation or a quadratic equation form looks like? Good. Okay. Now I'm going to, just so we keep it in one variable, I'm going to write it as ax squared plus bx plus c equals 0. But graphing it, obviously the 0 would be the y, right? Okay, so there's some things that we have to talk about. There are some restrictions on a, b, and c that we need to realize. We are going to say that a, b, and c are elements of your real numbers. Okay. Now, let's think about this. If a was 0, what would happen to that first term? It'd be 0, right? Essentially, it disappears. We would not write 0 plus bx. We would just write plus bx, or positive bx, right? And that would then turn this thing into what kind of equation? A linear equation. Okay. So we need to make the condition that a cannot be 0, else it takes us back to a simpler type of equation. Okay? So everything that we deal with today, and really a lot of the stuff that we learn today over the next couple of days, is going to be something that we then transition into how we deal with cubic equations, which would be like ax to the third type stuff. And then what we learn with squared and cubic is going to take us into 4th degree. And we keep going all the way up to whatever degree you want, but the underlying principles for solving any degree polynomial equation that we want start here with quadratics. Okay, so this is, we're going to spend a lot of time dealing with this. Yes? So that E is the phrase, or stands in for the phrase, is an element of, or belongs to. Okay, I like to think of it as belongs to, but you should read it as element of. Okay, so there's going to be some techniques that we go through throughout the next couple days on how to solve some quadratic equations. Now, some of these techniques are repetitive, meaning I might be able to do technique 1 on something, but also technique 4. Okay, and we might just have to sit and think, okay, for me, technique 1 might be easier, or technique 4 might be easier. Okay, technique 3 up there is the exact same thing as technique 4. Okay, and I'll explain that and show that to you in the next couple of days. Ultimately, by Thanksgiving, I should be able to give you any polynomial equation. So that's anything like ax to the whatever plus bx to the whatever plus cx to the whatever. I should be able to give you any of those where those whatevers, those exponents are all integers, positive integers, and you should be able to factor it, okay? But the idea is you want to factor it efficiently, okay? So there's going to be a hierarchy of steps that we go through. And the one thing that we will try to do, first of all, is look for a GCF. Are there any greatest common factors? Does everything divide by 2? Does everything divide by 3 or whatever, okay? And we'll see if that makes things easier for us, and then we'll get into specific techniques of factoring after that, okay? Okay, so factoring, obviously, this one here, we're thinking, you know, if we start with ax squared plus bx plus c equals 0, we're trying to get down to something like mx plus, I'm going to write d times nx plus f, something like that equals 0. So you take your original quadratic equation and you break it down to 2 binomials that multiply together to give you that. Does that make sense? Okay. Let's think about, just real quick, make an analogy here of some simpler things. And I think if you can understand these simpler things, it makes the more complex algebra a little bit easier to manipulate. If I look at that, okay, the a, b, and the c, those are going to be real numbers. X is going to be a number that I'm not aware of, but it's still a number, right? So I'm taking, essentially, ax squared is just going to be a number, bx is just going to be a number, and c is just going to be a number, right? Well, those numbers need to all add up and give me what? They all need to add up and give me 0, okay? Now, let's do this. Let's say that, let's not even pay attention to the 0 over here. Let's look at just the left-hand side. Like, let's just say this was a quadratic expression, and I wanted to factor it like this, okay? This stuff over here on the left, the stuff that I've highlighted, is just going to be what we call a composite number. You guys know what composite numbers are? Think about it this way. Think about, you know what a vowel is and a consonant in your alphabet? Okay, so you know your vowels, you know your consonants. So those are 2 different types of letters, right? So in mathematics, we have the same thing, but for numbers, we have composite and we have prime, okay? So your prime numbers are numbers greater than 1, okay, that are divisible only by themselves and 1, right? Okay. Composites are numbers greater than 1 that are composed of a series of prime numbers. Okay, so like 4 is composite because it's 2 times 2. 6 is composite because it's 2 times 3. 24 is composite because it's 2 times 2 times 3. Right? Makes sense? Or 2 times 2 times 2 times 3. Okay? We cool with that? So what I've got highlighted up there represents a composite number. Okay? So let's say it's 24. Can I rewrite 24 as 2 times 12 or 3 times 8 or 4 times 6? Can I do that? Is that still 24? And that's all I'm doing right here, guys, is that I'm rewriting a composite number times a product of 2 things. So if I tell you I have 24 and one of the factors is 3, how do you go through and find the other factor that goes with 3? You divide 24 by the factor that you know, right? So if I know one of my factors for what's in yellow here, how do I find the other one? I divide the yellow thing by the one factor that I know, right? So when they ask you to find factors, or they ask you go through the factoring process, what you're really doing is that you're dividing. Okay, it's division. Think about what is the inverse of division? Multiplication. What do I do with this bottom line here, mx plus d times nx plus 5, if I want to get back to the yellow? Multiply. You call it FOIL, right? Okay. And FOIL says, essentially is a mnemonic device or a phrase that tells you first times first, so I take that number, mx times nx, outside times outside, so I take mx times f, and if you think about what you just did there, you distributed mx to nx and f, right? And then you do the same thing with d, you distribute it to nx and f, and when you distribute, all that is multiplication, right? So when I'm working and when they say factor, you're dividing. When they say distribute or FOIL, you're multiplying. Okay, so they're just keywords for those operations. Okay, The square root property. The square root property is another technique that is, it's actually only going to work on certain occasions, and it only works when the b term equals 0. So we'd be looking at something like a, I don't even want to write a right now. I'm just going to write like x squared equals c or something like that. Basically what's going to happen is that you're going to try to isolate your x squared term because there is no x term. You should be able to move your constants to one side. You should be able to divide both sides by whatever a was, and then you get this statement here. So it might be like x squared equals 9. Well, then I'll square root it, and I get x equals 3 and negative 3, right? Or I might get x squared equals 12. I square root it, I get x equals, 2 radical 2. Okay? Or no, sorry, 3 radical 2. Okay? Is that okay? Not 3 radical 2. What is radical 12? 2 radical 3. I got it backwards. Okay. So, does that make sense? You guys remember doing that? Okay. Complete the square. We'll talk about that down the road. I'm not going to write anything for that. You guys remember the quadratic formula? Okay. So there's your quadratic formula. Okay. Now, the one thing that people forget a lot is that it is a formula, so there's an equal sign in it, and you're solving for x. Okay? A lot of people just say opposite b plus or minus b squared root b squared minus 4ac over 2a, right? But you got to have that x there, and that's going to be important because eventually that technique will be used for solving like higher degrees, like x to the 4th, x to the 6th, x to the 8th, those types of things. And that x might actually be x squared, or we might be solving for x to the 4th, and we have to do something else after that. So we have to know what we're solving for. In trigonometry, we might actually be solving for like cosine there, or cosine x, or tangent x, or something like that. So we need to know what our variable part is that we're solving for. But that's our quadratic formula. Okay. Now that is a shortcut. A lot of your formulas are shortcuts for a procedure that you had recognized, or that people way before us had recognized. Hey, I'm doing the same thing over and over and over again for these types of problems. Let's create a shortcut and see what that leads us to. Okay, so they started with something like ax squared plus bx plus c equals 0, and what they ended up doing is they completed the square on it, because that's really the way we factor things. We complete the square. And if I used a, b, and c instead of specific numbers, it actually, through the process of completing the square, generates that formula. Okay, so we will do that either tomorrow or the next day. It depends on when I can find the time in class to work that in. But we'll talk through the derivation of the quadratic formula. Did you guys ever do that last year? Did you do it? Huh? Learn? All right. How many solutions can a quadratic equation? Let's talk about this. What is the image of a quadratic? If I were to graph it, what do we call it? Parabola. Okay, so we call it a parabola. And when we talk about our parabola, we've got a couple different ways that they can be orientated. So I'm going to start with like ax squared plus bx plus c equals 0. Okay. In all these pictures, a is going to be positive. Okay. A can be negative and will be negative a lot, and especially in the applications that we work with in the next couple of days. But if A is positive, remember we're talking about concave up and concave down. If A is positive, your graph is going to be concave up. And that's the general picture of a parabola that most people kind of think about. So there's my parabola. Does that make sense? Okay. Now that's coming from, the A, the B, and the C can be different values. And if you guys remember anything about transformations last year, they can take whatever, depending on what A, B, and C are, they can move that graph left and right. They can move it up and down. They can reflect it horizontally, and they can reflect it vertically. Okay, so there's some things that we can do with A, B, and C that are going to transform that graph, but there's no way that you can get away from that graph with ax squared plus bx plus c, no matter what A, B, and C are, from being a parabola. Okay, it's going to have that U shape to it all the time. Now, remember what we talked about the other day. If I'm graphing an equation, this side here is a graph, and that side there is a graph, correct? Now, y equals 0 would be the graph, so we'd be looking at that thing right there, correct? That's essentially the second graph. And remember, when solving an equation, what we're trying to do is see where does the graph of the left-hand side intersect the graph of the right-hand side. And when I say where, I'm referring to the x value. Does that make sense? So it's the x value essentially where the y values are identical. Well, where does that happen here? To where the parabola crosses the x-axis, right? Okay, so what we're going to have here is the number of solutions we're looking at is 2 real solutions for that particular type of parabola. Okay, you could have something, you don't need to draw this one, but if A was negative, that blue one would maybe be my parabola. Still intersecting twice, right? Okay, so when you guys work through these problems and you get 2 answers, you are ultimately indicating that your graph should look like one of those 2 things right there. Is that okay? All right. So solving a quadratic equation, a lot of times we call them like roots or zeros or x-intercepts. Those are all synonyms. Now, there are appropriate places to use the word root over the word x-intercept, or the word zero over the word root, or whatever. I don't really care, as long as you know that they're all meaning those positions on the x-axis where the graph crosses. All right, so that's one situation. What if we adjust the A, B, and C in some manner, and we'll talk later on what the adjustments have to be to create something like this. But we can adjust things so that our graph does something like that. So there our graph is tangent to the x-axis. You guys remember what tangent means? Touches one time. Okay, we talk about in geometry about circles. Okay, but it doesn't have to be circles. It could be anything that is a curve. Can be tangent to really anything else that is either a line or a curve as well. Okay. How many x-intercepts would you have there? You would have 1. So 1 real solution. Okay. And I'll just give you kind of an example of what this would look like. If you ended up with something like that factor down to like x plus 2 times x plus 2 equals 0. Because those are the same thing, that indicates that you have what we call a double root. And in this case, that double root would show up at -2. But that means that we'd be tangent to the x-axis there. Does that make sense? Okay. Or you could rewrite that as x plus 2 squared. That's the idea that we have one real solution. But algebraically, analytically, by hand, it's going to show up as one answer redundant twice. Does that make sense? Okay. So we're going to have 2 solutions. We can have 1 real solution, or we can have, anybody know the next option? No solutions. So think about what's going to happen. Think about what your graph should look like. If we're saying solutions are based on how many times the graph crosses the x-axis, my parabola in this picture better not what? Better not touch the x-axis. So Let's say that my parabola looks like that, and that's going to be what we refer to as let's write it this way. We'll go 0 real solutions. But when I have 0 real solutions, that automatically leads me, okay, and I'm going to use this. So when I see an arrow like this, that means if and only if, okay, basically like it's a two-way street. So 0 real solutions actually tells me I have 2 non-real solutions. Okay, or if I had 2 non-real solutions, that automatically tells me I had 0 real solutions. Does that make sense? Okay. Does anybody know what my non-real numbers look like? If they're non-real, they're kind of like maybe some Andrew's friends. Imaginary. You guys remember your imaginary numbers? So if they're imaginary, okay, or non-real, that means that they have somehow incorporated a negative number underneath the radical, right? And I'll just put -1 here. And that incorporates I, right? Okay. Now, do you remember what this thing, and there's some notes later on that will fill us in again, but do you remember what that thing is called in your quadratic formula? Huh? Discriminant. Okay. What does it mean to discriminate between things? Yeah, you're looking at characteristics that separate things, right? Okay. Or categorize things. Well, b squared minus 4ac takes those 3 images there, 3 potential graphs, and discriminates based on how many real solutions there are. So if that is negative, that number underneath the radical there, as my discriminant is negative, I'm going to have that picture all the way to the right. If that number is 0, I'm going to have that picture in the middle. And if that number is positive, you're going to have that picture on the left. Say again? Yes, so the C value tells you where you're going to intersect the y-axis. That's your y-intercept. Depending the structure that you have your quadratic equation written, whether you have it in what we call vertex form or we have it in standard form. Okay, so if it's in that form, that's vertex form. So A times the quantity x plus h squared plus k. If it's in that form, then the k, or what you're calling c, would show the up or down movement. But if it's in this form, if it's in ax squared plus bx plus c form, the c is just telling you the y-intercept. All right, so let's talk about what I believe our textbook calls the zero factor property. I don't use that term very much. I usually call it the zero product property. But I mean, if you're talking about factors, you're talking about products, right? Okay. I've just learned it in pretty much all textbooks that I've ever experienced in pre-calculus, advanced math, college algebra. They always use zero product property. This one's the only one I've seen call it zero factor property. But what it says is if, okay, so it's a property, but we can write it as an if-then statement. It says if A times B equals 0, then, can't spell, then A or B must be what? I'm taking a number times a number and getting 0. what does one of those numbers or both those numbers have to be? Has to be 0. Okay? That's the zero property. Okay? That makes sense, right? That's what we know multiplication by 0 always gives me 0. So, let's put that thing to use. Let's talk about this example here. Okay? Now, in order to do anything that we are going to do in this course, factoring wise, applying theorems, that kind of thing, you need to make sure that your particular example, your specific problem, mimics the thing that we've been doing. Okay? So does this mimic a quadratic equation that we want to be able to factor, that we can factor? What does this number here have to be when you want to factor? 0. So you always need to replace it and put it in a quadratic equation, the general form for quadratic equation, which is ax squared plus bx plus c equals 0. So when we do that, we get that, correct? All right. Now, think about this. And I'm just going to highlight the left-hand side. When you choose x, okay, and this process is going to choose the correct x for us, but let's just say I choose x to be any number. Let's say 2. So I have 4 plus 10 minus 1, so it would be negative 10, right? Are there numbers that multiply together to give me negative 10? Is negative 10 a composite number? Yeah. Okay? So depending on what x is, that thing on the left is going to be composite. Well, if it's composite, doesn't that mean I should be able to figure out the two things that multiply together to give it? Does that make sense? Okay? Now, you guys have always used in the past, and this is what we're going to use here, a technique that says, I'm going to call it the product sum technique. And this is the point of the class, guys, where I know you know how to do this. And we're still going to talk about it because I think I need to show you why you go through the process that you go through. You look for two numbers that multiply together to give you what here? Negative 24. And they should add up to give you what? They should add up to give you 5. What are those two numbers? Positive 8 and negative 3. Okay? So now, that basically breaks down that yellow. So if that yellow number was a composite number like 10 or negative 10, now we've written it in red there as like 2 times 5 or something like that. Does that make sense? It's still 10, but it's in a different version, different format. Okay? Now, here's my question. Is that even though it's in parentheses and it's a binomial, is it a singular object? Yes, and that's the way we want to think about things in parentheses, right? So that's a singular object, kind of like A up here is a singular object, right? Is this a singular object? Kind of like B up here is a singular object, right? Are those two things that are highlighted on the bottom, x plus 8 and x minus 3, are they being multiplied together like A and B are being multiplied together? Okay. Do they both equal 0? Okay. So, if you guys remember, back to geometry, we talked about the law of detachment. If we have a specific, that's a terrible highlighter, but if I have a specific case right here that mimics the condition or the hypothesis of an if-then statement, you can then take your specific example, x plus 8 and x minus 3, and you can attach to it the conclusion of your theorem. Okay? So, what does that allow me to do? It allows me to say, okay, if this is happening, if this mimics that, then x plus 8, which is essentially this A, must be 0. And this x minus 3 then, which is essentially the B, also must be 0, or could be 0 as well. Does that kind of make sense on why we do that? I think in the past, you're just taught do this, okay? But the reason we do it is because we have two numbers we're multiplying together. and their product is 0. So that must mean one or both of them is 0 themselves. So that gives me x equals -8 and x equals 3. Those are two real solutions. So now I know where my graph crosses the x-axis. I know where it crosses the y-axis based off what my C term was, and we'll get into that later as well. We'll revisit that. But that's the product sum technique. Now, it's something you guys knew how to do, right? I could give you that problem day one, and you could have gotten the answer, okay, because you know the procedure, you've seen them before. But now I want you to understand that those underlying principles that allow us to really work with that procedure. Now, does anybody know why we multiplied two numbers together to give me C and add to give me B? Does anybody know why that works? Well, let's talk about that. So let's write down. Let's do it in. Do I have gray? No. I'm going to write down ax squared plus bx plus c equals 0. Okay? That's my general quadratic formula, right? Or form. Okay? General quadratic equation format. We're going to factor that. So when I factor that, and actually, because this product sum technique only works when a is 1. So let's get rid of that x, or sorry, that a in front of x squared. Let's make it 1. If it was a, we use, you guys remember the AC method? Okay. The AC method and the proof of that, if we have time later in the week, it's exactly the same as this. It's just a couple more variables. We have time, I'll show you how that kind of works out and how that's proven. But I'm going to factor this, and we factor that, it's always going to be down to something like this. X there and X there, right? And it's going to be plus or minus, but because I'm going to use arbitrary values, I'm going to put plus. And because it's an arbitrary value, then it could take on a positive number or a negative number, depending on whatever it is. Okay. Now, because I don't know what B and C are, I don't know what's going to go in those numbers or those positions, right? So I'm going to introduce another set of variables. They're just unknown values. I'm going to call them M and N. Okay. So we're saying based on what B and C are, it can factor to x plus M times x plus N. We've seen many examples where that happens, right? Now, if I have it factored like this is x plus M times x plus N, can't I undo that factoring, undo that division through multiplication? So let's multiply this out real quick. Let's FOIL this. If I FOIL this, I get x times x, which is x squared. I get M times x, which is mx, right? I get x times n, so I'm going to write that as nx again. And I get m times n, right? Is that okay with everybody? Okay. What do you recognize about those two terms in the middle? They both have an x in them. Okay, they are like terms, right? I can group these two, and I can rewrite this as x squared plus m plus n times x plus mn, right? Okay. Now, if x squared plus bx plus c equals 0 was factorable across m and n like this, using those values of m and n, then this here should be the same exact thing as that, right? Does that make sense? Well, if I look at c, if these two things are the exact same thing, that and that should be the same thing, except for the mn is now a product of two things that should multiply together to give me c. Does that make sense? Okay, so I can make that argument that two numbers that are multiplying together to give me c. Do these two numbers are they the same m and n? Are they being added together right there to give me that coefficient? Does that coefficient link back up to that b? Yeah. So that's the logic behind why we multiply two numbers together to give me c, but they add up to give you b. Okay. Does that make sense? Have you ever seen that before? Okay, but does that help you think? When I was in school, I was never shown. It wasn't until I took time on my own to recognize that, realize that, and whether that was in high school or college or whatever. But and I knew what I was supposed to do, but I always, why does that work? I was always intrigued by, why does that work? Does anybody want to be an engineer? Nobody in this class wants to be an engineer? Holy crap, that's never happened before. I usually ask people who wants to be an engineer, and like 30 hands go up, and I ask, well, what kind of engineer I want to be? Oh. But engineers are people that want to know how things work, right? Okay. Mechanical engineer, civil engineer, that kind of stuff, computer engineer. They want to know how things, mechanical, they want to know how things work. Electrical. I want to know how things work. Okay. So that's kind of the way I'm going to teach things. Is that all right? Okay. No homework tonight. Okay, we will have homework tomorrow.